Welcome back for your next dose of Calculus 6.1, Day 2, Estimating with Finite Sums. We're going to take the things that we learned earlier and we're going to try to extend so we can find the area for more exotic shapes, not necessarily just trapezoids and rectangles and circles. So let's get started. Much about what we know about dinosaurs is learned from the fossilized remains of their skeletons. And other traces of their existence, fossilized tracks, fossilized gastroliths, and fossilized coproliths, although I think for those last two, saying fossilized is a little bit redundant. Taking a measure of skeletal bones gives scientists an estimate for the normal dimensions of these prehistoric beasts. So we're going to use area as an accumulation of rate. Use area to accumulate as an accumulation of rate works great for most straightforward geometric shapes. However, if the function takes on a more exotic shape, then we really don't have a way to find that area. However, we do have a way to estimate that area with pretty much our most basic shape, the rectangle. So here is the speed function for a Parasaurolophus P38NT as it decelerates over 15 seconds. So we can see that its velocity is decreasing. And it says down over here, well, you're supposed to draw 3 equally width rectangles with heights equal to the speed of the P38NT on the left side of the interval. And that first one has been done for you. I'm going to zoom in here just a little bit, and we see that this first rectangle, the height matches the rectangle perfectly on the left side. So for this second rectangle, we're going to want the height to match perfectly on the left side. So let's draw that rectangle. And then we'll draw the next rectangle, which is also going to match on the left side. And as I'm looking at these rectangles, I'm going to mentally note that the area of these rectangles is greater than the area under the curve. So in my head, I'm thinking already that if I find the area of these rectangles, I'm going to overestimate the distance that the P38NT is going to run during these 15 seconds. Okay, so let's get moving to this next one. To calculate area, I really recommend that you organize your data in a chart with columns for every interval and rows for width, height, and area. You're going to estimate the height of your rectangle and you're going to complete the chart. So this first rectangle was done for you. Let's go back to that first rectangle. And you'll notice that the time goes from 0 to 5. So over here, we have 0 to 5 as the interval. The next rectangle has time that goes from t equals 5 to t equals 10. So you'll notice over here, 5 to 10 is the width of this rectangle. So the interval just gives you where the rectangle starts and where the rectangle ends. Where is the left side of the rectangle? Where is the right side of the rectangle? From what I'm seeing, all the rectangles, 10 minus 5 and 15 minus 10, they all have a width, delta t, of 5. The next thing we want to do is to estimate the height of those rectangles. So let's estimate the height of those rectangles. This first one, this looks like it goes to about 21.5. And this one over here, this one goes up to about, let's call that 17. Depending on how you see it, you might have different numbers there. The last part of this chart is to write an expression for the area of that rectangle. I don't think you necessarily have to compute it, but you definitely should be writing an area formula. They're all rectangles, so the area of all of these rectangles is the width times the height. This gives me 5 times 21.5 and 5 times 17 for those areas. Now the estimate for the distance traveled by P38NT is just going to be the sum of all of these rectangular areas. So the distance is going to be equal to 5 times 23 plus 5 times 21.5 plus 5 times 17. Now remember, you may not have 21.5 and 17 depending on how you choose to estimate those rectangles. Putting on the teacher hat, I need to tell you that this expression that we just wrote, where the distance is the sum of 3 products, this is something that people look for when they grade your AP test, and probably when they grade your test at school. Writing down the sum of the products is always an excellent idea. That gives us a distance of 247.25. And remember, that's not the actual distance, that's an estimate of the distance. And furthermore, because the rectangles were bigger than the curve, this is an overestimation. So we can say that the actual distance that P38NT ran is less than 247.25 feet. Now, we use the heights of the rectangles to be perfectly bang on to the curve on the left side of the rectangle. And when that happens, we create something called a left rectangular approximation method. The left, because the height is perfect on the left side. Rectangular, because, of course, all the shapes were rectangles. And then approximation, because we're approximating the area, and it's not the actual area. So now, I think for this next problem, here is the Parasaurolophus data presented in a table. So these are the actual numbers now. And we're supposed to use a right rectangular method. So let's get going with the right rectangular method. I would encourage you to make the chart with the intervals. And then the next thing is to write down delta t. How wide is each one of these intervals? How many seconds is each interval? Of course, each rectangle is about 5 in width. And we want to do the height on the right side. So what I'm going to do is I'm going to highlight the number on the right side of the interval. And those highlighted numbers, that's where we're going to get the height of the rectangle on the right side of the interval. It's a pretty aptly named process. So let's figure out the height on the right side. What is the height when t equals 5? It is 21.6. Next interval. What is the height when t equals 10? It's 17.25. Last interval, what is the height when t equals 15? Well, it's 10.06. The next line of the table is to write down the area of each of those intervals. And I'm just going to write them as a product. I'm not going to actually do any multiplication just yet. Okay. The next part is the distance. So remember, we want to write the sum of all of those products. And then the last step is to grab your calculator and add all of that together. So our estimate for the distance that P. Parasaurolophus 38NT ran is 247.25. I mean 244.55. Bad math. Actually, I just looked this up, and my first number was wrong. It should be 307.5. So if you were pulling your hair out previously because I was giving you a weird number, I humbly apologize. I did get that one wrong. So here we go. We do know that the actual distance that Parasaurolophus 38NT that he ran is somewhere between 244 and 307 feet. Okay, that was quite an adventure. Let's move ourselves on to this next section, where we look at yet another rectangular approximation method. So this third rectangular approximation involves finding the height of the rectangle at the midpoint of each interval. So you might guess that this is going to be called the midpoint rectangular approximation method, and you would be correct. And at this point, we're going to mention that using a rectangular method doesn't have to be for velocity. It could be used for any other rates or any other tables or any other units. So we're going to use this for this problem here, where we have the section of a fossilized gallimimus femur, and it's measured for cross-sectional area at 7 different places. And you know, that's probably easy. You're just going to figure the diameter of the bone and get the area, the cross-sectional area based on the diameter of the bone, if it's reasonably circular, that is. So we're going to use what's called the midpoint rectangular method to estimate the volume of this femur. So here is our table. We've got the length. This is 0 centimeters from the left, 6 centimeters from the left, 12 centimeters from the left of the femur, 18 centimeters, 24, 30, and 36. And then these are the area at those different distances from the left side of the femur. So what we're going to do is we're going to create 12 centimeter cylinder sections of the gallimimus femur, kind of like what we're seeing in the illustration. Cylinder 1 over here on the left, cylinder 2 in the middle, and cylinder 3 on the right side. And to be honest, you don't even really need to think about those because we're just going to use a rectangular method, a midpoint rectangular method. Now to do this, we're going to have, in this case, we're going to need 3 rectangular sections, and they're going to go from 0 to 12, 0 to 12, 12 to 24, and then 24 to 36. Basically, we did 36 divided by 3, and we got 12. So same process. Let's figure out the length of each section. They all look to be 12. Next, we're going to look at the data in the center of the interval. So if the first interval goes from 0 to 12, the center of that interval should be 6. The second interval goes from 12 to 24, and if I know and I have to figure out what the midpoint of that is, the midpoint is at 18. And at 18, the cross-sectional area is 17 cubic centimeters. So we'll put a 17 there. And then the next section of the femur is from 24 to 36. And the midpoint of 24 and 36, that's going to be at 30. And the cross-sectional area at 30 is 17.8. So now we have our chart completed with information with the length of each rectangle and then the function evaluated at the midpoint of each of those rectangles. And so the rest of this just becomes, you know, what I'd like to say is disembodied mathematics. We're not going to really worry about the context so much as we're going to be worried about the data. So let's go ahead and get those volume expressions. Just like before, it's just a straight multiplication of the length and then the function. In this case, the function is the cross-sectional area. Write down the sum of the products. And that gives us 628.8 volume. And so this section of the gallimimus femur has an approximate volume of 628.8 cubic centimeters. Not bad. Time for us to look at some important ideas. The first one is this idea of the rectangular approximation method. And in a rectangular approximation method, we slice the region vertically and we find the area of each rectangle, or we use a rectangle to approximate the area, and then we just find the area of all of those rectangles. Rectangular approximations come in 3 varieties. They are the left rectangle, the right rectangle, and the midpoint rectangle. And the only difference between the three is where do you find the height of the rectangle. So I think it's time for us to check our understanding. We've got oil leaking out of a tanker that is damaged at sea, and the damage to the tanker is worsening, as evidenced by the increased leakage per hour recorded in the table below. A. Use a right rectangular approximation with 4 subintervals to estimate the amount of fuel leaked over 8 hours. Since the rate is increasing, is this approximation an over or an under approximation? I always say it's important for you to organize your data, so let's organize our data in a table. Now, we want 4 subintervals, so we need to, if we are, well, let's put it this way. If we're going from 0 to 8 and we want to split that up into 4, that means each interval needs to be a width of 2. Do some quick math to try to make that work, and yeah, it does kind of work. The width of each of these intervals is going to be, I think, 2 hours. And we want to find the height on the right side. So the right side, will highlight all of the right sides, and we'll evaluate the function at each of those highlighted numbers. So at t equals 2, the leakage rate is 97 gallons per hour. At t equals 4, the leakage rate is 190 gallons per hour. At t equals 6, the leakage rate is 369. And then at t equals 8, the leakage rate is 720. Next task is to go ahead and write out all of the products. Okay, and we're looking good so far. Now we're going to write down the amount of fuel leaked as a sum of all the products. And then we just have to evaluate. That gives us 2,752. About 2,752 gallons of fuel leaked in 8 hours. As to whether this is an over or an under approximation, the only thing, maybe not the only thing, but I recommend that you go ahead and you draw an increasing function, because this is an increasing function. Now that we've drawn an increasing function, we just need to make a couple of rectangles that are right rectangles. And 2 rectangles should be enough. Really, just 1 rectangle is going to be enough to see that the right rectangle is going to be an over approximation of an increasing function. Right rectangles are going to produce an over approximation of the area, maybe I should say, of an increasing function. So the true amount of fuel leaked is less than 2,752. Let's go on to part B. And this says to use a midpoint rectangular approximation to estimate the amount of fuel. Now we're going to do the same chart again. But this time we want to get the height at the middle of each rectangle. So for the middle of 0 and 2, we have 70. For the middle of 2 to 4, we get 136. To the middle of 4 and 6, we get 252. And the middle of 6 and 8, we get 516. So let's put all those values in our table. And then we will write down our area. Next, we're going to write down our sum of products. And then we just calculate. Okay, that gives us 2,382 and about 2,382 gallons of fuel leaked during those 8 hours. So that's it. That's our first section of Chapter 6 in Calculus. And, you know, these rectangular approximations, they seem like they are not very calculus-y, but believe me, there's not an AP test that goes by where you don't have to do a rectangular approximation. They are very important to our understanding of the next really big topic here in calculus. So really get to know and understand how to do all of these rectangular approximations. And with that, we'll see you next time.